Hi everyone, this is going to be a video walkthrough of problem 2. Let's begin by reading the prompt. So we are given the following extremely unbalanced search tree. And what's really important here is that this search tree is still a BST, right? So what it says is select the minimum number of rotations in the correct order required to balance this tree. Okay, so in essence, what we want to do intuitively is when I have this tree, we need to make it balanced, okay? So let's kind of like draw out the steps here. So I'm just going to first draw this exact same tree just in my handwriting. Okay, so this is our starting state. So what's our ending state, right? That's important to understand. So we need to make this tree balanced, right? That's what the prompt says. So this tree has 1, 2, 3, 4, 5, 6, 7 elements. So what it's going to look like when it's fully balanced, it'll look something like right? It'll look something like this tree because this is a completely balanced tree. So if I'm using the numbers from the red, we see that tree is going to look like 3, 1, 0, 2, 6, 4, 8. Okay, so this is the completely balanced tree, and we somehow have to go from the first one to the second one. Okay, so what's important here to notice is that these two trees, 1 and 2, aren't that different. They both have this piece that's the same, right? The only thing that we really need to worry about are these right here, okay? So that's kind of the intuition for how you can go about solving this problem. So with that in mind, we know that the rotation operations we need to do probably aren't going to be for these ones because they're in the same shape in the start and end. Instead, we probably have to do some sort of rotations with these, okay? But notice that if I do any sort of rotation with 4, it's a leaf, so it's not going to change anything. The idea is if you want to make a rotation that's actually going to change a tree, you want to do something to a potential parent, right? So the idea is that we want our tree to kind of move in this direction. So it kind of looks a little more balanced. So in order to do that, what I think we can do is we can do a rotate right. So the first thing we're going to do is going to do some rotate right. Let's do a rotate right. So if I do a rotate right on 6, let's just say I do a rotate right on 6. Intuitively, what's going to happen is that 6 will move down and 3 will fill the spot. But that's not really what we want to have happen, right? Instead, what we could do is we could do a rotate right on 8. What's going to happen here is 8 will kind of go down like this. Okay, so the first thing we can do is a rotate right on 8. So let's see what's going to happen after we do that. So after we do a rotate right on 8, it's going to kind of be this motion. That's like a rotate right motion. So 6 will fill the spot of 8, and 8 will go down here. Okay, so the next thing that we need to do is we need to get to this final state. And you may be wondering like, oh, how many more rotations do we need, right? So notice that when we look at both of these states, the only difference here between the top state and the bottom state is that 6 is the child of 3. You guys kind of see that in the second image? So in order for 6 to be the child of 3, what we need to do is a rotate right on 6, right? Because if I do a rotate right on 6, then 3 will come here, and 6 will be a child of 3. So that's the next thing we're going to do. We'll rotate right on 6. And what is that is going to look like is that here's how I kind of like to think about it. This is the original state. So when I do a rotate right on 6, we're kind of doing this motion. So what's going to happen is that 6 becomes the child of 3, okay? And then we also have to deal with 4 and 8, right? So 4 used to be connected to 3. Now it's going to be connected to 6, which makes sense because 4 is in between 3 and 6. So if I set it as the left child of 6, that relationship is preserved, and then 8 will stay as the right child of 6. And then we can see our tree is fully balanced, and the 2 steps we did were rotate right on 8 and rotate right on 6. Okay, so that's all for this part. I hope you all enjoy this video walkthrough. Oh, actually, we'll do part B as well. Okay, so looking at part B, it says which of the following 2, 3, 4 trees are an accurate equivalent to the above left red black tree. Okay, so notice here that in this class, we usually deal with left-leaning red black trees, but it's completely valid for us to also look at 2, 3, 4 trees and their equivalents to red black trees. Okay, so when I'm looking at this red black tree, whenever I see a red node, what that means is that red node is glued to its parent. Okay, so if I'm looking at this tree, notice that we get B, F, J at the top, right? And then we have A, right? This relationship is here. And then we see that D is between B and F, so we'll put D here. And then we see in between F and J are G and H. So we'll put G and H right here. And then G we know is glued to H because G is the left red child of H. And then we see that K goes to the right of J. So this is the answer for the corresponding 2, 3, 4 tree. And we see that it looks like option B. So we can select B. And I believe that is all, yeah, for problem 2. I hope you all enjoyed this video walkthrough and stay tuned for the next part.